Please subscribe to support the channel. You ask, how long would it take us to go to Mars? And it sounds like there should be one clean answer, like a flight time on a ticket. But the moment you look at the actual physics, the question falls apart. The time is not fixed. It depends on when you go, how you go, and what you count as the trip. If you don't pin those down, how long is basically undefined. So let's strip this down very directly. First issue, the distance to Mars is not constant. Mars is not sitting at one fixed number of kilometers away from you. It is orbiting the sun, and so is Earth, and both are moving all the time. When Earth and Mars are on the same side of the sun, lined up well, the distance can drop to around 55 million kilometers. When they're on opposite sides, the distance can be more than 400 million kilometers. If you average over time, you get a number around 225 million kilometers. But that average never matches any specific mission exactly. So when someone tells you Mars is X million kilometers away, the immediate follow-up should be, on what date? But even that is not the full problem. You are not starting from a parked platform in space, you are starting from Earth, which is already moving around the sun at about 30 kilometers every second. That motion is not optional, you are stuck to it. When you launch, you don't suddenly turn that off and point directly at Mars like aiming a laser. Instead, you add speed to what Earth already has, and you use that to move from Earth's orbit to a new path that reaches Mars's orbit. In simple terms, you are changing your path around the sun, not driving across some empty gap in a straight line. So the question, how long to Mars, really means how long does it take to move from Earth's orbit to Mars's orbit, starting from a moving planet. Now comes another important detail most people ignore. Are you asking about the time the spacecraft spends cruising between planets, or the time for the whole mission, door to door, from leaving Earth until you are back on Earth again? If you only look at cruise time, you get answers like 6 to 9 months for a typical efficient path. That is usually what you hear in popular science. It takes about 9 months to get to Mars. But space agencies planning human missions do not think in 9-month chunks, they think in years. A realistic human Mars mission looks more like this: many months going out, a long stay on the surface while you wait for the next good return alignment, and then many months coming back. That total can easily reach 2 to 3 years. So if you ask how long to Mars, and you really mean when do the astronauts get home, the answer jumps from months to years. And you still do not get to choose those months whenever you like. This is the next trap in the question. You cannot just say, let's launch in April. It's convenient. The alignment between Earth and Mars only gives you efficient paths at specific times. Because Earth goes around the sun faster than Mars, it slowly catches up. And about every 26 months, there's a good window where an efficient transfer is possible. Those are the classic Mars launch windows. If you miss that window, you either wait more than 2 years for the next one, or you accept a much more expensive and usually less practical trajectory. So when you ask, how long to Mars, hidden inside that is, are we leaving in a proper window, or are we trying to fight the orbits and pay the price in fuel and complexity? That brings us to the part that actually decides everything under the hood. How fast are you willing to go, and how much are you willing to pay for that speed? In rocketry, speed changes have a name, delta V, which just means change in velocity. Every time you want to go faster or slow down later, you need delta V, and delta V always costs propellant. If you choose the classic efficient trajectory, you accept a slower, roughly 8 or 9 month cruise, but you save on fuel. If you try to cut that down to say 4 or 5 months, you need a much higher departure speed from Earth, and then you arrive at Mars going faster too, which means you need more braking to slow down into orbit or land. All of that extra speed translates directly into more propellant at launch, more mass, bigger rockets, and more money. The painful part is that the relationship is not gentle. You don't get a linear deal where cutting the time in half only costs you a bit more fuel. Because of how rockets work, every extra bit of speed makes the propellant requirement grow rapidly. You add more propellant to go faster, but that extra propellant itself has to be accelerated, which needs even more propellant, and so on. Very quickly, you hit a point where going much faster just isn't practical with current technology. That is why even today, most Mars mission concepts using chemical rockets are still talking about roughly the same range of transit times, many months, not weeks. So now look back at the original question with all of this in mind. How long would it take us to go to Mars? Do you mean at the closest distance or the farthest? With a minimal energy trajectory or a high energy, high risk one? Counting only the cruise out or the entire mission until the crew is back on Earth again? Leaving in a proper launch window or trying to brute force it at a bad alignment? And how much fuel, money, and risk are you willing to trade for shaving a few months off? Once you see all those hidden choices, the question stops being a simple number and turns into a design problem. Time to Mars is not fixed by some single rule. It is set by the distance on that specific date, the path you choose through the sun's gravity, the propulsion you use, and the safety limits you impose on the crew. Change any of those and the answer changes. But that raises a new and sharper question, and this is where the tension really starts. If Mars is just over there in our solar system, why does it sometimes feel like it's practically next door and other times like it has vanished into nowhere for years at a time? If distance was all the factor, you'd expect a clean, simple answer. But as soon as you look at how Earth and Mars actually move, you see why the timing of your launch is as important as the power of your rocket. First, you need to accept one basic thing. You never fly in a straight line to Mars. There's no point-and-shoot path where you just aim and fire. Both Earth and Mars are locked into orbits around the Sun, and those orbits are not perfect circles. They're slightly stretched, which we call ellipses. Earth completes one lap in about 365 days. Mars takes about 687 Earth days for one lap, so they're constantly changing their positions relative to each other. When you go to Mars, you're not crossing a gap in empty space. You're moving from one orbit around the Sun to a different orbit around the Sun, and that shift automatically takes time. Now, if both planets are moving at different speeds, the obvious next question is, how often do they line up that actually help you? This is where something called the synodic period comes in, and the idea is simple even if the name sounds heavy. Because Earth moves faster, it slowly gains on Mars. Roughly every 26 months, Earth has caught up enough that the angle between them and the Sun is just right for an efficient transfer. That 26-month rhythm is the drumbeat of Mars missions. Those are the classic Mars launch windows, and almost every serious Mars mission is built around one of these windows, not a random date picked for convenience. So when people say, why aren't we just launching all the time? The answer is because the orbits don't care what your schedule is. They set the dates, not you. Next, let's talk about the actual distances involved during these different configurations, because that's the part that really hits your travel time. When Earth and Mars are lined up on the same side of the Sun in a configuration called opposition, the distance between them can drop to around 54 to 60 million kilometers. That's about as close as you ever get, and that's when you want to launch if you care about efficiency. But when the geometry is bad, when they're on opposite sides of the Sun or just poorly placed, the separation can blow up to around 400 million kilometers or more. Same planets, same orbits, completely different gap to cross. If you try to stick with efficient trajectories, that huge change in distance translates directly into months more time in transit. For a good window, you're in that classic 6 to 9 month range. For a terrible alignment, if you insist on going, your options are either accept a very long cruise or spend huge amounts of fuel to brute force a faster path. And in practice, most mission designers simply wait. That's why you see Mars missions come in clusters around certain years, and then long, quiet stretches. Now here's another key point most people don't realize. When you launch, you do not aim your rocket at where Mars is on that day. You aim at where Mars will be months in the future. If your ship will take, say, 7 months to get out to Mars's orbit, then you need to predict where Mars will be 7 months from now and design your trajectory to intersect that point. Every Mars mission you've heard of has done exactly this. It's a long, calculated intercept with a moving target, not a direct shot at the current visible position of the planet. Think about what that really means. When the rocket leaves Earth, Mars is not in front of it, waiting to be reached. Mars is somewhere else in its orbit, following its own schedule, and your spacecraft has to time its arrival to hit the same spot at the same time. That is why navigation and timing are so precise. A tiny error in launch speed or direction can turn into a miss of thousands of kilometers by the time you arrive at Mars's orbit. This brings you to the too early, too late problem, which sounds simple, but actually drives a lot of the mission design. If you leave too early, your spacecraft gets to the intersection point before Mars does, and Mars is still behind you. If you leave too late, your spacecraft reaches that region of space after Mars has already passed, and now the planet is ahead of you. In either case, if you really want to salvage the mission, you need large correction maneuvers, which means more burns, more fuel, and more risk. And here's the catch. That correction fuel is not free. You had to launch it off Earth. So if you want the option to fix a too early or too late arrival, you must plan for that propellant from the beginning, which increases your launch math from day one. The more you try to give yourself wiggle room, the heavier, more complex, and more expensive the mission becomes. That's why realistic missions are designed to hit tight windows with tight trajectories. You simply cannot afford to be casual about timing when every kilogram of fuel has been dragged out of Earth's gravity well. So you end up with this uncomfortable conclusion. The geometry of the orbits does not just decide where Mars is, it quietly sets the realistic lower limits on how fast you can go there with sane fuel budgets. You can try to cheat a little with higher energy launches, but you cannot escape the basic pattern. Sometimes Mars is effectively next door, and sometimes, for practical purposes, it may as well not exist as a reachable target. And that raises the next, sharper question that cranks the tension up even more. If the orbits, the timing, and the distance curves are all fighting you, then why do you keep hearing this calm, simple answer that it takes about 8 or 9 months to get to Mars? Where does that number actually come from, and what kind of path is hiding behind that number? Because it is not random, and it is not the best we can imagine. It's the best we can afford with the kind of rockets we actually fly. The core idea is something called a Hohmann transfer. Don't worry about the name. The idea is simple. You start in one circular orbit around the Sun, roughly where Earth is. You want to end up in another, larger circular orbit where Mars is. The most fuel-efficient way to do that with a short, clean maneuver is to change your path into an ellipse that just touches Earth's orbit at the inner end and Mars' orbit at the outer end. You do one big burn near Earth to drop into that ellipse, you coast along that ellipse, then you do another burn when you reach Mars' orbit to match speeds with Mars. 2 main burns. That's it. It sounds almost too simple, and that's why people sometimes underestimate how important it is. In deep space mission design, that Hohmann-style transfer is the standard reference. It's not flashy, it doesn't give you record-breaking speed, it's basically the minimum energy option between 2 circular orbits. And because fuel is heavy, and heavy is expensive, a path that minimizes energy is incredibly valuable. That's why when you look at Mars mission designs, so many of them are built around something very close to this pattern, with only small tweaks for the actual window and exact orbits. So why does this particular path give you that famous 8 to 9 month travel time? If you work through the orbital mechanics for the real distances of Earth and Mars, you can figure out how long that elliptical path takes. You don't have to do the math yourself, but here's the key idea. The transfer orbit has a certain year length around the Sun. You're only flying 1/2 of that oval from the inner end to the outer end. For the Earth-Mars case, that half ellipse works out to a few hundred days of flight, typically in the ballpark of about 240 to 270 days, depending on the exact alignment. That's roughly 8 to 9 months. So when someone says it takes about 9 months to get to Mars, what they're really saying, without all the detail, is if you use a near Hohmann transfer between Earth orbit and Mars orbit in a decent launch window, your cruise time will be around 8 to 9 months. It's a shorthand for standard fuel-efficient path with current-type rockets, not a law of nature. But here's the uncomfortable follow-up. What if 9 months feels too slow? What if you say, let's make it 6 months or 4? Can you just push harder, leave faster, and arrive sooner, like stepping harder on a gas pedal? This is exactly where the cost starts climbing sharply. To beat the Hohmann time, you need a more energetic trajectory. In plain terms, when you leave Earth, you must have a higher speed relative to the Sun than the Hohmann solution gives you. That extra speed lets you get out to Mars's orbit sooner, so travel time shrinks. But to get that extra speed, you need more delta V at launch, a larger change in velocity, and every extra chunk of delta V costs you propellant. This is where the rocket equation quietly ruins your day. It says that the speed change you get from a rocket depends on how much propellant mass you start with compared to how much mass is left when the tank is empty. And that relationship is not straight. It uses a logarithm. In straight talk, that means if you want a little more speed, you need noticeably more fuel. If you want a lot more speed, the fuel requirement grows very fast. Doubling the speed change does not double the fuel. It can explode the fuel mass into something you simply cannot launch. You end up designing a ship that is almost all tank and almost no useful payload. And remember, arriving faster is not free either. If you throw yourself at Mars on a high-energy trajectory and show up going much faster relative to the planet, you then have to slow down more aggressively to get into orbit or land safely. That slowdown also needs delta V, which means even more propellant carried all the way from Earth, or more extreme use of Mars's thin atmosphere, which pushes your heat shields and structures much harder. So let's just shave a few months off quietly turns into let's completely redesign the rocket, the mission, and the risk profile. That's the theory, but how does it look in real missions we've actually flown? Take NASA's Perseverance rover, for example. It launched in late July 2020 and landed on Mars in mid-February 2021. That's about 7 months of cruise, right in that expected range for an efficient transfer in a good window. Other recent orbiters and landers like Mars Reconnaissance Orbiter, MAVEN, and earlier rovers like Curiosity also sit in a similar band, roughly 6.5 to 9 months in transit. The exact number shifts with the launch date and the chosen trajectory, but they all cluster around that Hohmann-style solution. So when you look at the scoreboard of actual robotic missions, you don't see wild variations like 3 weeks or 3 years of cruise with normal rockets. You see a tight band that matches what the basic Hohmann physics predicts, with minor adjustments. That's not a coincidence. That's the cost of propellant, launch mass limits, and risk pushing you toward that same family of orbits again and again. There's one more important piece here, and it goes against your everyday intuition. On the way to Mars, most of the time, your engines are off. You do the main burn near Earth to set up the transfer orbit. You may do some small course corrections along the way, and then another major burn when you arrive. The rest of the trip, you're not driving in the sense that a car or a plane is constantly powered. You are in free fall around the sun, following the path set by gravity and the initial push you gave yourself. That's why just floor it all the way there is not how deep space works. To keep thrusting for months, you would need to carry the propellant for months of thrust, and your rocket would become enormous. So instead, you pay up front in 1 or 2 big burns. Then you let gravity do the shaping. The pace of the trip is controlled by the orbit you are on, not by a continuous engine push. And with chemical rockets, that orbit naturally lands you in that many-month time frame. So now you can translate the famous simple answer. How long to Mars? If the person is talking about a typical, efficient chemical rocket mission launched in a good window, the honest shorthand is something like 8 or 9 months of cruise because we're basically using a Hohmann-type transfer. But that immediately raises the next hard question. If that is the normal, physics-driven answer for robots, what does the scoreboard of all our Mars flights really look like? And what does that imply for sending humans who need far more protection and support? So at this point, you've heard the theory. Hohmann transfers, 8 to 9 months, efficient orbits. But talk is cheap. The real test is simple. When we actually launched hardware at Mars, how long did those trips take? Did anyone secretly do it in 3 months and just not brag about it? When you look at the scoreboard of real missions, the pattern is brutally clear. Go back to the early days, missions like Mariner and Viking. These were not built with today's fancy computers or materials, but the basic orbital mechanics were the same, and the engineers were already playing the same game. Their cruise time sat roughly in that 6 to 9 month range, sometimes closer to 200 days, sometimes closer to 300, depending on the exact launch window, the chosen trajectory, and how much energy they were willing to pay for. As you move forward to more modern orbiters and landers, you see the same thing again and again. Different rockets, different payloads, different countries, but the cruise time keeps clustering around that 200 to 300 day band. That cluster is not an accident. It is what you get when you use chemical rockets. You care about mass and money, and you stick to sane launch windows. Now focus in on one of the most famous recent examples, Perseverance. This was not a tiny probe. It was a heavy, complex rover plus its entry, descent, and landing system, launched on an Atlas V5. It lifted off in late July 2020 and hit the Martian atmosphere in mid-February 2021. That's about 203 days of cruise, a bit under 7 months. It covered hundreds of millions of kilometers in that time. But again, remember, the distance traveled along the orbit is larger than the simple separation between Earth and Mars. The important part is not just the raw number of days, it's how that number was chosen. Mission designers picked an energy, something called characteristic energy or C3, that balanced three things: the performance of the rocket, the mass of the spacecraft, and the arrival conditions at Mars. If they had chosen a much higher C3, they could have shaved some time off the cruise, but the rocket might not have been able to loft the full payload, or the arrival would have been too hot and fast to handle safely. If they had chosen a much lower C3, the trip would have taken longer and the arrival might have been gentler, but the spacecraft and mission schedule would pay for that extra time. The final choice, around 7 months, sits right in the sweet spot for current chemical rockets and realistic science payloads. Then you look at a mission like Europe's Rosalind Franklin rover. It's not even flying yet, but the plan gives you another hard data point about timescales. The current roadmap targets a launch in 2028 and arrival at Mars in 2030. That doesn't mean 2 straight years of cruise, but it does show you something important. Agencies think in terms of full campaign timing, not just a single transfer segment. You have cruise, Mars orbit insertion or landing, surface operations, relay support, sometimes aerobraking or long orbital reshaping. The total arc from we depart Earth to we are stable and operating at Mars stretches well beyond the simple cruise time number. You see that mindset in the planning documents. They're managing years, not months. Now, maybe you're thinking, okay, but this is all government stuff. What if you really pushed it? Couldn't you do a crazy fast 3-month sprint if you really wanted to? On paper, yes, people have worked out trajectories that could get a spacecraft from Earth to Mars in under 90 days. These are very high-energy ballistic transfers. You pour a lot more speed into the departure, you accept a much higher arrival velocity, and you either burn a huge amount of propellant to slow down, or you smash into the atmosphere very aggressively and trust your heat shield and structure to survive. The problem is not that physics forbids these fast paths. The problem is that flying them with real hardware and real budgets is brutal. The departure energies you need is far beyond what we usually buy with today's heavy lift rockets. Your launch vehicle has to throw a very high-speed payload, which means either a much smaller spacecraft or a much bigger rocket, often both. And then at the Mars end, the high-speed arrival magnifies all your risks. Thermal loads go up, G-forces go up, error margins shrink. So far, nobody has signed off on paying that price for an actual mission. Instead, every real Mars mission sits in the compromise zone between what is physically possible and what is financially and technically sane. And this is where the scoreboard becomes a warning for human missions. Look at what we've actually done. Small probes, big orbiters, heavy rovers, landers with complex entry systems, all launched by different rockets from different nations, all ending up with cruise times of roughly 6 to 9 months for efficient windows. These robots do not need food, water, air, radiation shielding, or psychological support. They don't complain, they don't get sick, and if they fail, it is a financial and scientific loss, not a human tragedy. If even those missions, with their lower safety requirements and simpler life support needs, still end up in the 6 to 9 month corridor, what does that really tell you about a future human ship? A human Mars vehicle is basically a small moving habitat. It needs pressurized volume, radiation protection, robust life support, redundancy, food, water, waste systems, medical gear, exercise equipment, tools, and backup systems for all of that. All of that adds mass, and mass is the enemy of high-energy trajectories. With the same basic propulsion technology, chemical rockets, a human ship is going to be heavier, not lighter, than the robotic missions we fly today. Heavier spacecraft need more energy to reach the same speeds. More energy means more propellant. More propellant means even more mass. You can see the loop forming. The idea that we would somehow take a much bigger, more complex, more fragile system and push it on a dramatically faster trajectory with the same underlying engine tech is not realistic. You can tighten the numbers a bit with clever staging, refueling, or high-energy windows, but you are not jumping from 7 months down to 1 month without changing the propulsion game completely. So when you read off the scoreboard, the message is pretty blunt. Physics and engineering have already told us what the natural Mars travel time looks like with chemical rockets and sane budgets, and it sits in that multi-month range. To move far away from that, you have to pay in rocket size, in mission cost, in risk, or in all three at once. And that should trigger the next harder question in your mind. If the normal chemical rocket game keeps us stuck with months of transit even for robots, what happens when we deliberately try to go faster? How much extra speed can we realistically buy? How much calendar time can we cut? And what kinds of new dangers do we create when we choose to shave those months off? Here's the hard question. If we know a Hohmann-style trip takes something like 8 or 9 months, why not just push harder and get there in half the time? If we can build giant rockets and stainless steel starships, shouldn't Mars be a 3 or 4 month ride instead of a slow cruise? This is where you start hearing numbers from SpaceX. They've talked about Mars trips in the range of roughly 80 to 150 days, with an average around 115 days, using high energy transfers and very carefully chosen launch windows. In simple terms, that's trying to cut the classic Hohmann time by about half. On paper, that looks amazing. You keep the same basic chemical propulsion, you upgrade the scale and the refueling strategy, and you squeeze the trip down to about 3 to 5 months instead of 8 to 9. But look at what that really implies. To pull off an 80 to 150-day trip with chemical rockets, you are not doing a gentle minimum energy ellipse anymore. You're leaving Earth with a lot more speed relative to the Sun than a standard transfer needs. That higher starting speed doesn't come from nowhere. It comes from more propellant, more powerful engines, more stages, and in SpaceX's case, multiple refueling flights in Earth orbit just to fill the Mars vehicle before it even leaves. The ship becomes huge, the launch campaign becomes complex, and the energy you're buying at the start echoes through every part of the mission. Now ask the next question. What is the actual penalty for saying, I'm in a hurry, let's do 3 or 4 months instead of 7? To hit that kind of time, your spacecraft has to leave Earth with a much higher excess speed above escape. Once you've paid the cost to climb out of Earth's gravity well, any extra push you give it shows up as more speed relative to the Sun. Even a modest increase above escape speed translates into a big bump in your cruise speed across the inner solar system. The problem is the cost curve. To get that extra departure speed, you don't just add a little propellant. Because of how rockets work, each increase in target speed demands a larger and larger fraction of your starting mass to be propellant. You use propellant to accelerate propellant, which then has to be lifted off Earth in the first place. The fuel bill doesn't grow gently, it ramps up hard. So going from 9 months to, say, 5 months is already expensive. Pushing down toward 3 months is worse, and trying to push down toward 1 or 2 months with the same chemical engines becomes almost absurd. You either end up with a ship that is mostly fuel and almost no payload, or a rocket stack that is so big and complex that it stops being practical. Engineers like Robert Zubrin have looked at this in detail and tried to find a middle path. They've proposed faster, non-Hohmann trajectories that still use chemical rockets but accept higher energies. In some of those profiles, you aim for a roughly 6-month trip instead of 8 or 9. The idea is straightforward. You do a stronger initial burn to leave Earth faster than a pure Hohmann transfer. And then, when you reach Mars's orbit, you do a stronger braking burn to slow down enough to be captured. It's still a 2-burn scheme, but both ends are more aggressive. This gets you there sooner, but notice the price you pay. You arrive in Mars's neighborhood with a higher relative speed that must be removed somehow. Either you carry more propellant all the way to Mars for that heavy braking burn, which increases your launch mass and complicates your staging, or you rely more heavily on Mars's thin atmosphere to slow you down, which increases stress on your heat shield and structure. In both cases, the mission becomes more sensitive to errors and your margins get thinner. Faster is not just same mission, shorter time. It's different mission, higher stakes. And that brings us to the human side of high-energy arrivals. When you hit Mars at higher speed, the entry is harsher. The heat shield sees more intense heating. The structure feels higher deceleration loads. The guidance and control systems have less time to correct any deviation. For robots, that's already scary. For humans, you have strict limits on how many Gs you want the crew to feel, how much risk you'll accept in thermal protection, and how much margin you insist on every critical system. It doesn't stop at arrival. To get those higher speeds at departure, you also have stronger burns leaving Earth. That means higher G loads on the crew during launch or departure stages, more stress on the vehicle, and tighter constraints on engine performance. You're trading calendar time directly for physical stress on both people and hardware. Every month you shave off the cruise phase shows up as more intensity at the beginning and end of the mission. So where does that leave a realistic, fast, but not crazy future? Looking at everything we know about rockets, mass, and human limits, the near-term plausible range for fast human Mars missions is something like 4 to 6 months in transit, not 30 days, not a long weekend sprint. That 4 to 6 month band is already very ambitious. It assumes large, reusable launch systems, orbital refueling, optimized windows, and a willingness to accept higher energies than classic conservative designs. Even then, you're still living in deep space for a huge chunk of a year, soaking up radiation, dealing with microgravity, and depending on systems that cannot fail. And that's the real punchline here. Even when you push hard with high-energy trajectories, your prize is shaving a few months off a journey that is still measured in months, not days. You don't turn Mars into a quick trip unless you completely change the propulsion technology. As long as you're using chemical rockets and you're trying to keep the mission even remotely reasonable in size and budget, the physics keep dragging you back into that multi-month regime. Which leads straight into the next uncomfortable question. If going significantly faster already forces us into huge rockets, complex refueling, higher G loads, and tougher thermal environments, what is really holding us back? Is it our navigation, our courage, or is it something deeper and more fundamental in the rockets themselves that caps how fast we can cross that gap? Here's the part most people underestimate. Before you even start thinking about how long to Mars, you have to win a brutal fight just to get off Earth. And the numbers in that fight decide almost everything that comes after. You're not starting from zero. You're starting at the bottom of a deep gravity well, and there's a hard speed scale baked into that well whether you like it or not. For Earth, that speed scale is escape velocity, a bit over 11 kilometers per second at the surface. That doesn't mean your rocket instantly jumps to that speed. It means that in energy terms, you need to reach that level of freedom before you are truly on your way into deep space. In practice, rockets do this in stages. They burn for several minutes, they shed empty tanks, they keep pushing until they have enough speed to stay in orbit instead of falling back. Low Earth orbit itself is already around 7.5 kilometers per second sideways. Then, to go beyond that and head for Mars, you add more speed on top, a few extra kilometers per second. By the time your Mars ship is genuinely free and moving on its solar orbit, you've stacked a huge amount of velocity on it, piece by piece. That is the energy price of just getting into the game, before you talk about going fast or slow to Mars. So the obvious next question is, what actually sets the limit on how much speed your engines can give you for a given amount of propellant? Why can't we just build a more powerful chemical rocket and punch out even harder? This is where a concept called specific impulse comes in. Think of it as a measure of how efficiently a rocket engine turns propellant into thrust over time. The higher the specific impulse, the more push you get out of each kilogram of propellant. Chemical rockets are capped in a pretty narrow band here. The best of them, using liquid hydrogen and liquid oxygen, are up around 400 to 450 seconds. Many practical engines sit lower in the 300-something range. That's it. There's no secret chemical mix that suddenly jumps you to 3 or 4 times that efficiency. The physics of chemical reactions and hot gas expansion put a hard ceiling on how fast you can throw the exhaust out the back. And that ceiling matters because the total speed change your rocket can deliver is tied directly to that efficiency number. If your exhaust is only leaving so fast, there's only so much total push you can extract before you run into insane fuel fractions. With current chemistry, you hit a wall where trying to add more and more speed just turns the vehicle into a giant flying tank with a tiny useful payload sitting on top. You can scale the rocket bigger, but you don't escape the underlying math. So what is that math actually saying to you in plain language? This is where the famous rocket equation from Tsiolkovsky comes in, like a quiet judge. It tells you that the total change in speed your rocket can provide is equal to your exhaust speed multiplied by the natural logarithm of your starting mass divided by your final mass. You don't have to write that down. Just pay attention to the word logarithm. That one word is the killer. A logarithm grows slowly. That means if you want to double your available change in speed, you do not just double your propellant. You need your starting mass to be much larger compared to your final mass. That usually means your ship becomes mostly propellant and structure with a tiny slice left for payload. The more speed you demand, the more violently the fuel mass grows. This is why Let's Cut 9 months to 1 month with the same tech collapses when you look at the numbers. You'd need a ridiculous amount of propellant and staging to give a Mars ship that kind of delta V, and almost nothing would be left for the actual crew habitat, life support, and cargo. You can't negotiate with that equation, but you can work around it a bit. The classic tricks are staging and, more recently, on-orbit refueling. With staging, you accept that the bottom part of the rocket is dead weight once its tanks are empty, so you drop it. That resets your mass ratio in your favor and lets the upper stages squeeze more useful speed out of their own propellant. With refueling, especially in low Earth orbit, you can launch your Mars ship mostly empty, then top it up with tanker flights to where it's solar orbit. That way, the deep space stage doesn't have to fight all the way out of the atmosphere with full tanks. It only has to climb with part of its load, then gets filled once it's already high and fast. SpaceX's Mars demands lean very hard on that second idea. They imagine launching a big reusable ship to orbit, docking multiple tankers to fill it completely, and only then doing the burn that sends it towards Mars on a high-energy path. This doesn't break the rocket equation, it just plays it more cleverly, spreading the punishment over several launches instead of one impossible mega rocket. But the core relationship is still there. Even with refueling and staging, if you try to push the delta V too high, the propellant, infrastructure, and cost explode. And that brings you to the bottom line, and it's not comforting. As long as we're stuck with chemical rockets with specific impulses in the low hundreds of seconds, the rocket equation will keep Mars travel times in the range of months, not days. You can trim the duration, you can aim for 4 or 5 months instead of 8 or 9, but you pay dearly in mass and complexity. You do not get a scenario where you suddenly cruise to Mars in a long weekend with the same kind of engines we're bolting onto rockets right now. So the real constraint on how long to Mars isn't just distance or orbits or courage. It's the fundamental efficiency of the engines we're using and the brutal math that ties speed to propellant. And that leads straight to the next hard question. If chemical fire and smoke lock us into this months, not days regime, what happens when we switch to something fundamentally different, like nuclear or electric propulsion? Does the clock finally start to bend in our favor, or do we just hit a new kind of limit? So if chemical rockets lock you into this months, not days regime, the obvious next move is to ask, what happens if you stop burning chemical fuel altogether and change the engine itself? If the problem is efficiency, can we just swap out the engine for something that throws mass out the back much faster and finally start to squeeze the clock? The first serious upgrade people look at is nuclear thermal propulsion. Instead of burning fuel and oxygen to make hot gas, you run hydrogen through a nuclear reactor. The reactor heats the hydrogen to very high temperatures. The hydrogen expands and blasts out the nozzle, and you get thrust. The key gain is this. For the same general thrust system, your exhaust leaves faster, which means your specific impulse almost doubles compared to many chemical engines. In plain terms, that means each kilogram of hydrogen you throw out gives you more speed change. You can use that in two ways. Either you keep the same propellant mass and get more delta V, which lets you fly more energetic, shorter trajectories, or you keep roughly the same delta V and shrink the propellant mass, which lets you carry more payload. For Mars, the interesting option is obvious. You try to push for more delta V and cut the transit time. People run the numbers and see potential for shaving weeks, maybe a couple of months off a typical Mars trip for the same overall launch mass. That is not a miracle jump to 30 days, but it is a real hard improvement. Then there is nuclear electric propulsion, which is a different beast. Here, you do not use the reactor to heat propellant directly. Instead, you use it to generate electrical power, and that power runs electric thrusters, like ion or Hall effect engines. These engines don't throw a lot of mass per second, but the mass they do throw is accelerated to extremely high speeds, so the thrust is low, but the efficiency is very high. The result is a slow, continuous push over months instead of a short, violent burn at the start. With nuclear electric, your ship leaves Earth slowly, builds up speed steadily, and can potentially change its trajectory more flexibly along the way. Over a long mission, you can accumulate a very large total change in velocity, much more than you could practically get from a single chemical burn. That opens the door to faster or more adaptable profiles, especially for cargo vessels that don't care as much about trip duration or crew comfort. You can design routes where you accelerate for a long stretch, then flip and decelerate, shaping the path as you go. We've already tested part of this picture with ion engines on robotic missions. Spacecraft like Deep Space One, Dawn, and others have used ion drives to reach impressive speeds relative to the sun. They prove the concept: continuous low thrust with very efficient propellant use. A few tens of kilograms of xenon can give you large changes in speed over the course of a mission. But look at what they need to run. They pull a lot of electrical power. On a human ship, that means either very large solar arrays or a nuclear reactor. Both options add mass and complexity. Then add the shielding you need to protect humans from the reactor's radiation, plus all the regular life support. Suddenly, the total system you need to support continuous electric thrust at human scale is heavy and non-trivial. So even though ion engines are real and have already flown, scaling them up to something that can push a crewed Mars vehicle fast enough while keeping humans safe from the engine's power source and deep space is not something you just do next year. It is a big engineering jump. Then there are the truly aggressive ideas, the ones you see in advanced studies and concept papers. Fusion drives, beamed power systems with huge lasers or microwaves pushing light sails or beaming energy to vehicles. Antimatter concepts. With those, on paper, you can design Mars trips that last 30 days or less. The physics doesn't immediately forbid that. If you can throw mass out the back at a tiny fraction of light speed, or if you can push a craft with external power without carrying all the reaction mass and energy on board, the rocket equation stops crushing you in the same way. Suddenly, high delta V becomes manageable, and trip times begin to collapse. But here's the catch, and it's a big one. These systems are nowhere near ready for human flight. Fusion for propulsion is still a research dream. Practical beamed power infrastructure for interplanetary travel is science fiction level expensive and complex right now, and antimatter is completely out of reach for large-scale use. So yes, the physics says maybe. The engineering says not even close. So why, even in papers that talk about nuclear options, do you keep hearing numbers like around 6 months instead of 30 days? Because even when you upgrade propulsion, you run into other hard limits. You can only ramp up reactor power so far before your cooling systems, shielding, and structure become massive. You can only push human bodies so hard with G-loads on departure and arrival. You only have so much money and so many launches to assemble and fuel these systems. When teams try to put all of that into a realistic mission concept, they keep landing in the same territory. Transit times of a few months. 4, 5, 6 months. Better than 9, but nowhere near short hop. And that's the real point. Nuclear and electric systems can bend the time curve. They can make Mars somewhat closer in practice, but they don't magically flip months into days without a revolution in both engineering and infrastructure. You can chop off some time and increase flexibility, but you're still living in deep space long enough for radiation, microgravity, and isolation to become serious, mission-defining problems. Which brings us straight to the next question you cannot dodge, even if you solve the propulsion side and cut the trip to a few months. Can the human body and mind actually tolerate that time in deep space without paying a price that makes the whole mission pointless? So here's the part that makes all the fancy trajectories feel a lot less abstract. Your own body is running a clock on the mission, and that clock does not care how clever your orbital mechanics are. You can argue about Hohmann transfers versus fast transfers all day, but in the end, every extra day in deep space is another hit of radiation, another day of bone loss, another meal you have to pack, and another turn of the psychological pressure screw. Start with radiation. Space is not empty. It's full of high-energy particles from the sun and from outside the solar system. In low Earth orbit, like the ISS, Earth's magnetic field still protects you from a lot of that. Between Earth and Mars, you're basically naked. Every day you spend out there, the crew is taking a dose. It might be low per day, but it adds up, and it never goes to zero. NASA's Mars risk studies talk about the total radiation dose over something like a 3-year mission as a major constraint. You add up the months going out, the months on the surface with only thin protection, and the months coming back, and suddenly that dose is bumping into lifetime safety limits. Now combine that with solar storms. Most days the radiation level is just a steady background, but sometimes the sun throws a tantrum and you get a spike of high-energy particles. You can plan a storm shelter in the ship with extra shielding, maybe tanks of water around it, but you cannot hide from the fact that longer missions simply give you more chances to be in the wrong place at the wrong time. So when people say it's only a few more months, from a radiation point of view, that is not small. That is more spin on the roulette wheel. Then there's microgravity. On the ISS, astronauts float for 6 months at a time, sometimes longer, and they spend a lot of time every day exercising just to slow down the damage. Without gravity, your muscles weaken, your bones lose mineral density, your heart and blood vessels adapt in ways that are not helpful when you go back to a gravity field. And that's with quick emergency return options, constant resupply, and a huge support team on Earth watching every data point. Now, imagine a 6 to 9 month Mars cruise. Same microgravity, but no quick ride home, no regular cargo ships delivering spare parts, no easy medical evacuation. If you let the crew decondition too much on the way, you're delivering weakened people to a planet where they suddenly have to work in 1/3 gravity, in a suit, doing hard physical tasks right away. The longer they float, the more aggressive your countermeasures have to be, and the more mass and volume you need for exercise gear, medical support, and monitoring. So how long to Mars becomes how long can we afford to let their bodies degrade before they have to do real work on another world? Next, life support, or very simply, stuff. Food, water, oxygen, filters, spare parts, replacement components, medical supplies, all of it. If you double your transit time and you don't radically improve recycling, you roughly double what you need to bring, plus margin. Every extra month means more meals, more waste to handle, more wear on filters, more chances for something to break. You can use closed-loop systems to reclaim water and air, but those systems themselves need spares, maintenance, and backup plans. Mission planners can't just say, we'll cruise for 14 months instead of 7, no big deal. That choice inflates the mass you have to launch, the size of the ship, the number of refueling flights, and the risk that a single failure cascades into a life-threatening situation. There is a reason most serious concepts try to keep transit times under control, even if it means paying more in propulsion. Time is not free. It shows up as mass and risk. Then there's the mental side, which is easy to hand-wave away until you actually think about what it means. Months in a confined volume with the same small group of people, no way out, and a communication delay that stretches up to 20 or more minutes round trip. You don't get real-time conversations with Earth. You send the message, you wait, you get a reply maybe half an hour later. Every argument, every decision, every emergency is handled with that lag sitting in the background. That's not just a bit annoying, it changes how you feel about time. The trip out is not dead time. It shapes the crew's mental state when they arrive. If they show up at Mars exhausted, burned out, and on edge because the transit dragged on, your surface mission quality drops. You want them sharp when they land, not barely holding it together. So again, the number of months in transit is not just a line in a spreadsheet. It is directly tied to how effective your astronauts will be once they get where they're going. Now, put all of that together and look at the idea you sometimes hear from people outside the field. Why don't we just go slower? It will be safer. On the surface, that sounds reasonable. Lower speeds, gentler entries, more margin to fix things. But with radiation, microgravity, consumables, and psychology, slower is not automatically safer. Yes, extremely high-energy, ultra-fast trajectories are dangerous in their own ways, but dragging out the transit for extra months in deep space is also dangerous. You're trading one risk for another. In reality, there is a sweet spot. Too fast, and your engines, heat shields, and crew get hammered. Too slow, and radiation dose, deconditioning, and life support masks start to crush you. Serious Mars mission studies are basically trying to land in that middle zone where you're not burning absurd amounts of fuel, but you're also not leaving the crew floating between planets for half a decade. That's why the numbers keep coming back to a few months for transit, not as slow as possible. And once you see that your body, your supplies, and your mind all act like timers, all counting down while you cruise, the question sharpens again. If just getting there already pushes human limits this hard, what happens when you add the most dangerous minutes of the whole trip on top of that? The moment you hit Mars's atmosphere and everything has to work perfectly the first time. Here's the part nobody can pretend is just engineering details. If you decide to go faster to Mars, you are also deciding how violent the last few minutes of the trip will be. You don't get to separate cruise time from landing conditions. Your arrival speed is the direct consequence of the trajectory you chose months earlier. And when you finally hit Mars's atmosphere, every decision you made is waiting for you in the form of heat and g-forces. Start with the atmosphere itself. Mars does have air, but it's thin, only about 1% of Earth's sea level pressure at the surface. That sounds harmless, but it creates a nasty combination. It is dense enough that if you come in unprotected at interplanetary speeds, the heating will destroy you. But it is not dense enough to slow you down early and gently the way Earth's atmosphere can for re-entry. So you are in a bad zone. Too much atmosphere to ignore, not enough to treat as a soft cushion. That means your arrival speed matters a lot. If your trajectory brings you to Mars going slow by interplanetary standards, you still hit the atmosphere hypersonic, but the heating and deceleration loads stay in a range your heat shield and structure can handle, with reasonable margins. If you come in faster because you chose a higher energy, shorter transfer, the kinetic energy you carry scales up hard. All of that energy must be removed in a very short distance and time, mostly as heat in the shock layer around the vehicle, and as g-forces on the structure, and for crewed missions on human bodies strapped inside. So when you say, let's shave a couple of months off the trip, you are not just editing a number on a schedule. You are turning up the intensity of entry, descent, and landing. You're asking your thermal protection system to survive higher peak heating, your guidance to stay stable through a wilder ride, and your structure and passengers to survive more severe deceleration. You're moving stress from the middle of the mission to the front door of the planet. You can see this clearly in the way we handled Curiosity and Perseverance. Both of those rovers used what NASA called 7 minutes of terror to get from the top of the atmosphere to the surface. That sequence chained together a heat shield, a supersonic parachute, a powered descent stage, and a sky crane lowering the rover on cables. It sounds complicated because it is, but every part of that chain was designed around a specific arrival speed, a specific corridor of entry angles, and a specific heating and load profile. Their roughly 7-month cruise times were not picked at random. Mission designers chose transfer trajectories that delivered the spacecraft into Mars's atmosphere with conditions the materials, parachutes, and engines could realistically survive. If you shorten the cruise by pushing the transfer much harder, you'd have to redesign that entire system to deal with higher speeds and harsher entry. There's no free shortcut where you keep the same landing system but just fly faster and arrive earlier. Now, think about what changes when you put humans inside that system. A robot can tolerate higher G-loads, higher failure risk, and more edgy thermal margins. If it breaks up, it's a bad day for the project, but nobody dies. Humans have much tighter limits. You don't want the crew blacking out under huge G-loads on the way down. You don't want to run the heat shield so close to its material limits that a small manufacturing flaw becomes fatal. You also want lots of redundancy and controllability during descent. All of that pushes you towards calmer arrival conditions. Calmer arrivals mean lower relative speed at the top of the atmosphere, or more time to break into orbit and then land with a dedicated lander. Either way, that leans back towards trajectories that are not extremely high-energy sprints. In other words, just because you can design a 3-month robotic shot doesn't mean you should design a 3-month human shot with the same aggressiveness. Human-rated systems pull you back towards the months-long but not insane regime. This is one reason many mission architectures separate the big interplanetary ship from the lander. Instead of blasting straight down from interplanetary space to the surface, the main vehicle breaks into orbit around Mars first. That orbital insertion burn is big. You have to dump a lot of speed to let Mars's gravity capture you instead of slinging you past into a new solar orbit. Every meter per second of extra arrival speed makes that burn more expensive in propellant. And remember, all of that propellant had to be launched from Earth, boosted out of the gravity well, and carried across space. Once you're in Mars orbit, you can take your time, check systems, then send down a lander optimized for entry and touchdown. That spreads out the risk, but it also means you paid for the capture burn with fuel you carried all the way from home. If you try to get fast by arriving with very high speed, your orbital capture gets punishing. Either you accept a massive fuel budget for insertion, or you flirt with direct atmospheric capture maneuvers that are very hard to control and model, especially with humans on board. So you're stuck with a tight trade. Push the cruise faster, and you make the last minutes more violent and fuel hungry. Keep the cruise in the more moderate range, and the arrival becomes something your materials and heat shields can handle with more safety margin. And this is on top of everything your body and mind are already dealing with from the long journey. Once you see that, the question quietly changes again. It's no longer just how long to Mars. It becomes how much violence at arrival are we willing to accept in exchange for cutting a few months off the time spent in deep space. That's not just a physics question anymore. It's a risk and mission design question. And that sets up the next layer of the problem, because even if you find a balance for the trip out and the landing, you're still only looking at one leg of a much larger timeline. The mission isn't over when you touch down. You still have to survive on the surface, wait for the right window, and get home again. So the real question becomes not just how long does it take to get to Mars, but how does the entire mission clock add up when you include going, staying, and coming back? Here's the twist that most casual "how long to Mars" answers skip. Getting there is only about a third of the story. The flight out is just one segment of a much bigger clock, and once you plan a full mission instead of a one-way stunt, the numbers jump from months to years very fast. First, you have to pick what kind of overall mission you're even talking about. There are two big families people use: conjunction class and opposition class missions. In a conjunction mission, you accept a long stay on Mars, hundreds of days, so that both your trip out and your trip back line up with efficient launch windows. The idea is simple. You leave when Earth and Mars are in a good alignment, you arrive, you wait on the surface until the next good alignment for the return, then you come home on another efficient path. Your surface stay might be more than 500 days. It sounds long, but your outbound and inbound transits are both in that normal 6 to 9 month range with reasonable energy. Opposition missions do the opposite trade. Here, you try to keep the surface stay short, maybe only a few tens of days, and instead you accept more extreme, fuel-heavy trajectories for one of the legs, often the return. You might shoot out on a relatively normal transfer, land, stay a short time, then leave on a fast, high-energy path that swings you far from the sun and then back to Earth. That can reduce the time the crew spends on Mars. But now, the flight profile is more complex. The delta V goes up and the fuel bill explodes. It's a different flavor of pain. In both cases, the choice of architecture doesn't move you from years down to months. It just moves time back and forth between in space and on Mars. Then you see the aggressive studies that people like to quote, the ones that say you can do a full Mars round trip in something like 400 to 450 days, under 15 months total. Technically, yes, it's possible on paper. You design a trajectory that leaves on a good window, uses high departure energy, flies a faster than Hohmann transfer, takes a short stay on Mars, then leaves on another demanding route back to Earth. The clock from goodbye Earth to hello again can end up around that 400 to 450 day number. But look at the cost. Those concepts assume significantly higher energy on at least one leg, sometimes both. That means bigger rockets, more propellant, maybe more on-orbit refueling, and more violent arrival and departure conditions. Navigation margins get tighter, abort options get harder, and the whole mission moves into a more unforgiving regime. You basically spend a huge amount of engineering and money to pull the total time down from something like 3 years to just over 1 year. That is not a small gain, but it is not free, and it is not something you casually scale up for dozens of missions. Now compare that with the way NASA has often framed the problem in their long-term planning, the 3-year Mars mission picture. In that story, you have roughly a year out, a long surface stay while you wait for the right window, and then roughly a year back. The exact numbers change. Maybe it's 8 months out, 500 plus days on Mars, 8 months back, but the ballpark is close to 3 years door to door. That is the number that matters when astronauts and mission planners say, "How long to Mars?" and actually mean, "When do I see Earth again?" It's no longer a 9-month cruise. It's a 1,000-day expedition. And here's the key thing a lot of people miss. The long surface stay is not optional in those efficient architectures. You can't just drop people off, do a quick set of experiments, and bolt for home whenever you feel like it. The same orbital geometry that gave you your launch window from Earth also controls when it's smart to leave Mars for the return trip. If you try to ignore that and leave whenever, you end up on a bad alignment that costs you a lot more fuel, a longer flight, or both. So the time you're stuck on Mars isn't a random pause. It's baked into the mission from the first design step. You can pre-send cargo, you can park return vehicles on the surface or in orbit, you can build habitats in advance, but the crew still has to wait for the planets to line up again. That wait time is part of the how long, whether you like it or not. When someone imagines a quick out and back hop, they're quietly ignoring this orbital lock-in. This is why people talk about mission architecture like it's a kind of time machine. You can move time around, but you can't get rid of it. If you use something like a Mars cycler in the future, a big ship that constantly loops between Earth and Mars, you might reduce how often you need to launch new deep space vehicles, and you might give the crew a more comfortable, shielded environment for the transit legs. If you pre-deploy cargo with slow electric propulsion, you can send heavy stuff cheaply over longer periods and keep the crew vehicle lighter and faster. If you refuel in Mars orbit, you can adjust your return options, maybe allowing a different trajectory home. All of those tricks change how long the crew spends in deep space versus how long they spend on the surface, and how much industrial buildup you need in both places. But notice what they do not do. They do not turn a Mars mission into a short trip. The total door-to-door time for a serious expedition, with a crew that lands, works, and returns, is still in the range of years. You can tune whether that's closer to 400 days or closer to 1,000 days, but you are not getting it down to a few weeks without a totally different level of propulsion and infrastructure. So by now, the original question has been stretched almost to breaking. How long would it take us to go to Mars? If you mean launch to landing, maybe 6 to 9 months with current tech. If you mean launch to landing and then back to Earth, you're looking at a year and change in aggressive concepts, or close to 3 years in conservative ones. And all of that time is sitting inside the limits set by rockets, human bodies, and orbital mechanics. At this point, you might be tempted to ask one more thing. If we're spending years on this arc between planets and we're moving at tens of kilometers per second, does relativity start to matter? Do the astronauts actually time travel in any meaningful way? Or does all of this drama play out in almost exactly the same time frame for them as it does for everyone else watching back on Earth? So with all this speed, all this distance, do you at least get the sci-fi perk? Do you actually time travel on the way to Mars? Do you come back younger than everyone else in some dramatic way? Technically, yes. Practically, no. On a Mars trip, your ship is moving at tens of kilometers per second relative to the sun. Special relativity says when you move fast, your time runs a bit slower than someone who's standing still. But fast, in Einstein's sense, means a big chunk of the speed of light. Light is about 300,000 kilometers per second. You're doing maybe 30. That's 1/10,000th of light speed. At that fraction, the time dilation factor is so close to 1 that you need serious instruments to even see it. After a multi-month trip, the difference between your clock and a clock on Earth is in the order of microseconds to maybe milliseconds. That's millionths or thousandths of a second. You will not step off the ship feeling like you skipped ahead or lagged behind time. No interstellar moment. To you, the flight takes exactly as long as it feels. Then there's gravity, which adds another tiny layer. General relativity says clocks deeper in a gravity well run a bit slower than clocks farther out. On Earth's surface, you are deeper in the sun's and Earth's gravity than you are when you're coasting in interplanetary space. So in principle, when you head out, you climb to a region where time runs a hair faster because the gravitational pull is weaker. At the same time, your ship is moving relative to Earth, which tends to slow your time down. One effect makes you age slightly faster, the other slightly slower. For a Mars mission, both effects are tiny, and they mostly cancel or just sit at barely measurable. At the end of the mission, if you compare your wristwatch with a high-precision reference clock on Earth, there will be a difference, but it will be in the noise for anything human. Emotionally, you went away for, say, 900 days, and everyone on Earth also lived through about 900 days. But even if your body doesn't feel the relativity, the mission still has to deal with it in the background, because deep space navigation is a game of precision. When you're tracking a spacecraft over hundreds of millions of kilometers, you measure its distance and speed by sending radio signals and timing how long they take to go out and come back. Those timings are down in the nanosecond level for the accuracy you want. At light speed, an error of a billionth of a second is a few tens of centimeters. If your timing model ignored relativity and slowly drifted, those tiny errors would add up over months into real position and velocity mistakes. So the navigation systems that handle Mars missions do include relativistic corrections. They account for the motion of Earth, the motion of the spacecraft, the gravitational fields involved, all of it. Not because the astronauts will notice the time difference, but because a tiny timing bias can grow into a miss of kilometers when you're trying to hit a specific landing ellipse after 200 plus days of flight. For the onboard experience, relativity is invisible. For the guidance software and the tracking networks, it's another term in the equations they cannot ignore. The time warp that really matters to the crew is not Einstein's, it's psychological. On the way to Mars, the speed of light sets your communication delay. When Mars is relatively close, one-way light time is a few minutes. When it's far, it can be 20 minutes or more. That means a simple back and forth with Earth can take 40 minutes round trip. You ask a question, you wait, they get it minutes later, they think, they answer, you get their reply many minutes after that. There is no real-time conversation, no, hold on, let me Google that for you, in the moment. For day-to-day life, that delay stretches every interaction. A joke lands half an hour late. A problem on board can't be walked through instantaneously with ground control. Every decision feels more local, more isolated, because Earth is always lagging behind what's happening on the ship. That communication lag will shape the crew's sense of time much more than microseconds of relativistic aging ever will. Their subjective clock will be affected by waiting on responses, by long silences, by the feeling that they are always slightly out of sync with everyone back home. So no, you're not doing dramatic time travel on a Mars mission. Your heart, your watch, and your family's clocks all tick at almost exactly the same rate. But your experience of time is bent by distance and light speed in a way your daily life on Earth never prepares you for. You're always talking to a slightly older version of Earth, and Earth is always talking to a slightly older version of you. And that raises the next sharp question. If your own time stays almost normal, but your messages race ahead at light speed, what does that gap really look like? How much faster does your voice get to Mars than your ship? And why doesn't speeding up the ship do much to close that brutal minutes versus months difference? Here's a weird situation you almost never experience on Earth. On the way to Mars, your voice can be there while your body is still months away. Your radio message races across space at the speed of light, but the fastest ship you can realistically build crawls along in comparison. So you end up with this huge gap, minutes for signals, months for humans. The benchmark is simple. Radio waves are just light at different frequencies, and light in a vacuum is as fast as anything can go. When Earth and Mars are close, light can cross the gap in just a few minutes one way. When they're far apart, that one-way time stretches to 20 minutes or more. Double it for a round-trip conversation, and you're looking at up to 40 minutes between question and answer. That delay does not care who you are or how urgent the situation is. Nothing, no ship, no particle, no emergency instruction beats that speed limit. Now, compare that to the ship. Even with an efficient transfer, you're talking about 6 to 9 months of travel for a crewed mission using chemical rockets. Even with very optimistic advanced propulsion, you're still in the range of a few months. So you end up in this brutal ratio. Your message gets there in minutes, your body takes hundreds or thousands of hours. If you could somehow fly at a decent fraction of light speed, say a tenth of it, you could cover the Earth-Mars distance in under an hour. But we are nowhere near that. Our ships move at tens of kilometers per second, while light moves at hundreds of thousands of kilometers per second. We're under a 10,000th of light speed with current technology. This mismatch doesn't just make for fun trivia, it drives how missions have to be designed. Because you can't joystick a robot on Mars in real time from Earth. By the time you see what it did, the situation has already changed, and your next command won't arrive for many minutes. That's why Mars rovers move so cautiously. Planners send sequences of commands, the rover executes them mostly by itself, then sends back data, and the team adjusts the next day. It's a stop-go, batch-style operation, not a live video game. For humans, the same logic hits much harder. A Mars base or a crewed ship near Mars cannot rely on constant, instant advice from mission control. They can get guidance, procedures, and high-level decisions from Earth, but anything time-critical has to be handled locally. If there's a fire, a medical emergency, a landing anomaly, a power failure, you don't have the option to say, "Houston, talk us through this live." By the time their first sentence comes back, the event is already done, one way or another. That means the time delay between the planets becomes part of the mission architecture. It pushes you to design systems that are more autonomous, more fault-tolerant, and more understandable by the crew themselves. Your Mars base has to be able to diagnose and fix a lot of its own problems. Your software has to support decision-making on-site, not just log data for experts on Earth. Crew selection changes too. You're not sending hands who follow instructions. You're sending people who can act as their own mission control when they need to. Now look at the next natural thought. If our ships are the ones that are slow, can we fix this by just making them faster? If we cut the crews from, say, 7 months down to 3 or 4, does that do anything meaningful to close the gap with signals? The hard answer is not really. It changes the calendar, but it doesn't change the basic picture. Here's why. The light time delay depends only on how far apart the planets are at that moment. If Mars is, say, 200 million kilometers away during a particular part of its orbit, light is going to take on the order of 10 minutes to cross that gap, no matter how fast your ship can move. If you manage to have the ship's travel time overall, that just means you reach that position on the orbit earlier in your calendar. The signal delay when you're halfway there is still measured in many minutes. Unless your ship itself is moving close to light speed, the comparison will always be minutes for signals, months for ships. So even in a future where you have nuclear thermal or nuclear electric propulsion, where you shave a couple of months off the trip, the communication pattern doesn't really change. You still can't have normal conversations with Earth. You still plan around delayed responses. You still train the crew to operate with a lot of independence. Faster ships help with radiation, life support, and overall mission risk, but they barely touch the fundamental communication gap. That's the key point. The speed of light locks in a kind of minimum lag between planets that only changes as the geometry changes. Ship speed changes when you arrive, not how quickly news can travel in the meantime. So you end up with a strange split. Information moves on the scale of minutes, hardware and humans on the scale of months. Your decisions about mission design are trapped between those two timelines. And that tension hints at another question. If you can't beat the speed of light and you can't easily turn months into days, is there any way to work with the orbits themselves to make Mars travel feel more regular, more predictable, or slightly less punishing? Can you use clever orbital paths, reusable routes, or safety loops to hack the calendar, even if you can't change the fundamental speeds? So at this point, you've seen that you can't beat orbits, you can't beat the speed of light, and you can't cheat the rocket equation. So the next question is, if you can't change the rules, can you at least arrange the game board in a smarter way? Can you design orbits that make Mars trips more repeatable, safer, or cheaper, even if they don't actually make them short? One of the boldest ideas here is the Mars Cycler. Think of it as a giant ship that never really stops. It just loops between Earth and Mars over and over again on a repeating path. You don't fire it like a normal mission, send it once and park it. You set it up on a special orbit that regularly swings past Earth, then months later swings past Mars, then comes back to Earth, and so on a predictable schedule. You don't keep slamming big engines on the cycler every trip. You mostly let its orbit do the work. The heavy, expensive stuff stays in space. Things like radiation shielding, living space, long-duration life support, maybe spin sections for artificial gravity. When the cycler passes Earth, you launch a smaller taxi up to meet it, dock, ride it to Mars, then drop off in another taxi when it swings past Mars. On the return leg, you do the same in reverse. This can save you a lot of hardware over many missions because you're not launching a brand new deep space ship from scratch every time. You're reusing the big bus and only paying for the smaller, one-shot taxicraft. But here's the important part. A cycler does not break the fundamental timescale. The orbit that cycles between Earth and Mars still obeys the same basic geometry. The legs between planets are still on the order of months. The 26-month rhythm of good alignments is still there. You hacked logistics, not the calendar. So then you might ask the opposite question. Instead of focusing on reuse, can we design paths that give us a built-in safety net if something goes wrong on the way out? Is there a way to leave Earth, aim for Mars, and still have a natural way back without a perfect engine burn at Mars? That's where free return trajectories come in. The idea is simple but powerful. You pick an initial path so that if you never fire your engines again, gravity alone bends your course around Mars and sends you back toward Earth. If all goes well, you brake at Mars, capture into orbit, and continue the mission. But if something fails and you can't do that, the path naturally swings by Mars and returns home. It's an automatic abort option. Apollo used a version of this for the Moon. For Mars, it's harder because the distances are bigger and the sun's gravity dominates more, but you can still design trajectories with a loop-back property. The price is time and complexity. These paths are usually longer and less efficient than a direct high-energy shot. You might spend extra months coasting to make the geometry work. So again, you're trading calendar time for risk management, taking a slower loop to gain a safety margin if your propulsion at Mars fails at the worst possible moment. Then there's another class of ideas that aims at a different target. Not reuse, not abort safety, but fuel savings. The question there is, can you sneak up on Mars in a way that lowers the cost of capture, even if it takes longer? This is where ballistic capture concepts come in. In a classic fast arrival, you come in hot, then slam on the brakes with a big burn to let Mars grab you and capture you into orbit. In ballistic capture, you approach Mars more gently, often from behind in its orbit, and let its gravity and your careful trajectory slowly pull you into a bound orbit over a longer period. The capture is more like drifting into a parking spot than hand-braking into it. The advantage is clear. Your required braking burn at Mars can be much smaller, and your arrival conditions can be less demanding. That can mean less propellant carried all the way from Earth and more flexible launch dates, because you don't need the exact classic geometry of a Hohmann transfer. But here's the important part. A path to that gentle capture is usually longer. You spend more days or weeks in Mars's gravitational neighborhood, adjusting and waiting for the orbit to settle. For cargo, that might be fine. For humans exposed to radiation and isolation, every extra week is another risk. So when you put all these ideas side by side, cyclers, free returns, and ballistic capture, you see the same pattern. Time is not just something you suffer through, it's a resource you can spend or save. You can spend more time in cleverly chosen orbits to save fuel, to reuse hardware, or to give yourself abort options. Or you can burn more fuel and accept higher energies to save time and cut radiation exposure. Human missions will always sit somewhere on that sliding scale. Too far in one direction, and you get long, slow missions that are cheap on propellant but brutal on crew health and psychology. Too far in the other direction, and you get short, intense missions that are expensive, technically extreme, and unforgiving. The right answer is a compromise, tuned to the technology and risk tolerance of the era. And that brings up the next obvious question. With everything we know right now, our rockets, our budgets, and our risk limits, where are the serious players actually aiming? What transit times and mission lengths do NASA, ESA, and SpaceX really plan around when they stop making PowerPoint dreams and start drawing real hardware? So, after all the hypotheticals and what-ifs, what are the real numbers that serious space agencies are actually planning around right now? Not in sci-fi, but in project documents and hardware designs. If someone handed you a ticket for a Mars mission in the next few decades, what kind of timeline would actually be printed on it? Start with what we know best: robots. The current robotic baseline is very clear. Missions like Mars Reconnaissance Orbiter, MAVEN, Curiosity, InSight, Perseverance, and the orbiters from ESA in India have all flown with cruise times in the same band, roughly 7 to 9 months. Perseverance hit around 7 months. Others leaned a bit longer or shorter depending on the window and the exact trajectory. But nobody is doing 90-day Mars cruises, not even for uncrewed payloads with the rockets and propellants we use today. Upcoming missions follow the same pattern. When agencies plan new orbiters or landers, they still slot in cruise phases of several months. Launch in 1 year, arrive the next. You don't see official timelines with launch in June, land in August, using standard chemical launchers, because the energy and mass requirements would explode. That 7 to 9 month range is simply what falls out when you combine Hohmann-like transfers, realistic launch energy, and payload masses that make the mission worth the trouble. Now look at human mission studies. Different space agencies and research groups have run the numbers again and again, with different assumptions on propulsion, staging, refueling, and surface operations. When they aim for fast but still chemically driven concepts, they often land on total round-trip times around 400 to 450 days. That is launch to final return. To hit that, you usually accept high-energy trajectories, shorter surface days, more demanding burns, and more complex mission operations. On the other end, more conservative architectures, the ones that accept long surface stays and prioritize lower energy and more margin, still cluster near that 3-year mark you keep hearing, roughly 1 year out, 1.5 years on or around Mars, and 1 year back. The details change from study to study, but you keep seeing variations of about 3 years as the default story. It is a reflection of orbital mechanics, human health limits, and the desire not to push every single parameter to the red line at once. Then there is SpaceX's vision. When they talk about Mars transit times in the 80 to 150 day range, with an average around 115 days, they're not making up a fantasy number. Those trip lengths are aggressive, but they fit into the high energy side of what you can imagine with fully reusable chemical rockets, orbital refueling, and very well chosen windows. The idea is you don't send a tiny capsule, you send a large ship, refuel it in low Earth orbit using multiple tanker flights, and then commit to a powerful burn that puts you on a faster trajectory than a classic minimum energy transfer. In that context, 80 to 150 days is not impossible from a physics standpoint. The main challenge is practical. Can you build, reuse, and refuel vehicles at that scale with that reliability, and then handle the hotter arrivals and tighter margins that come with higher energy profiles? The bottleneck is execution, industrial capacity, systems engineering, and risk tolerance. If that ecosystem comes together, transit times could genuinely drop into the 3 to 5 month band for many missions. But even that fast future is still measured in months, not in days. On the more traditional side, Europe's Rosalind Franklin rover gives you another signal about how agencies think about how agencies think. The current plan points to a launch around 2028 and arrival around 2030. That doesn't mean 2 full years of cruise, but it does mean the overall campaign from launch, cruise, arrival, landing, checkout, and start of surface operations is spread over years. ESA and its partners are not rushing. They're treating Mars as a long-haul target with complex entry and landing systems, tight windows, and long planning cycles. That's the quiet message. Mars is not only physically far, it is organizationally far. To get a single rover to the surface, you're looking at development that spans over a decade, a launch and cruise phase of many months, and a science mission that runs for years if you're lucky. So when you ask how long to Mars in the context of national or international programs, the answer is longer. Put all of this together and you get a pretty clear picture for the next half-century. Barring a real propulsion revolution, the human Mars flights you're likely to see in your lifetime will almost certainly have several-month transit times each way, and total mission durations measured in years. Maybe fast, high-energy ships bring the one-way cruise down to 3 or 4 months for some missions. Maybe conservative missions keep it closer to 6 or 7 months. Maybe very aggressive architectures pull a round trip into the 400 to 450-day band. But you're not going to wake up and see 28 days to Mars as a standard offer with current tech. The numbers can tighten at the edges, but they're not going to collapse from months and years to weeks without a deep reset in engine technology, power systems, and space infrastructure. As long as we're flying big, crude habitats with chemical or near-term nuclear propulsion in the current launch environment, the answer stays in the same regime: a few hundred days out, a long stay, a few hundred days back. And that sets up the final, uncomfortable point you can't avoid. If the moon took 3 days and Mars takes years, what does that really say about where we are as a species and how far the jump is from we can visit another world to we can live and operate across the whole solar system? What does that time gap tell you about the real scale of the challenge ahead? Here's the part that really hits you. We went to the moon in about 3 days, but a real Mars mission might keep a crew away from Earth for something like 1,000 days. Same species, same basic physics, totally different scale. And that's your real answer to how long. The universe is telling you there's a huge difference between stepping just off the curb and crossing the whole street. Look at the number straight. Apollo astronauts traveled roughly 384,000 kilometers to the moon. With the Saturn V and a direct injection, they covered that in about 3 days. Mars, on average, sits around 225 million kilometers away. That's almost 600 times farther. Even if your path in space is not a simple straight line, that distance ratio sets the scale you're dealing with. When you stretch the distance by hundreds of times and you're still limited to tens of kilometers per second by your propulsion, the clock doesn't grow by a factor of 2 or 3, it jumps from days to months and years. So when someone casually says, "We did the moon in 3 days, why not Mars in 10?" The answer is because the numbers are not in the same league. The moon is still in Earth's gravitational and operational neighborhood. Mars is the next orbit out, across deep space, with nothing in between that can help you if something goes wrong. You haven't just extended the trip a bit, you've changed the class of mission entirely. That's why time ends up being the harshest constraint. Yes, fuel matters. Yes, money matters. Yes, public interest matters. But time sits over all of those. Every extra day the crew is spending in deep space adds radiation dose. Every extra day burns through consumables. Every extra day increases the chance that something breaks, a valve sticks, a sensor fails, or a tiny crack grows into a real problem. Psychological strain also grows with time. You're isolated, you're locked in a metal volume with the same people, you're dealing with delayed communication and the constant knowledge that you are months from home. So the question, how long does it take us to go to Mars, is never just about a travel time printed on a chart. It's really asking, how long are we willing to hold the crew and the ship inside that risk field? If you choose slower, low-energy paths, you save fuel, but increase the radiation and degradation. If you choose faster, high-energy paths, you reduce some time-based risks, but increase stress on structures, heat shields, and the crew's bodies during launch and arrival. Time is the currency you trade against all these other dangers. Now zoom out one level. If Mars is still months away, even with our best realistic propulsion plans, what does that say about everything beyond Mars? Think about Jupiter, Saturn, or way out in the Kuiper Belt. Travel times aren't just measured in years to decades with current tech. That's why Mars isn't just another destination. It's training. It's the test case for whether we can handle missions where the calendar, not just the distance, becomes the main enemy. If we can manage Mars, if we can run multi-year expeditions, keep people alive and effective, operate bases with delayed communication, and bring crews home safely, we've proven something critical, that we can manage time on an interplanetary scale, not just distance. Mars is where we learn how to run logistics, psychology, maintenance, and decision-making over years, not weeks. It's where we find out whether our systems and our societies can stay committed across timelines that exceed election cycles and attention spans. And here's the twist that should change how you think about the whole problem. The limit isn't imagination anymore. We've already drawn up serious design studies for fusion-powered drives that could, in theory, get you to Mars in 30 days. We've written papers on beamed power, advanced nuclear systems, exotic propulsion concepts that leave chemical rockets in the dust. On whiteboards and simulations, we can shrink the clock. The barrier isn't that we can't picture it, it's that we haven't built it. Right now, the real limiter is engineering maturity and willingness to pay. Do we invest in the massive infrastructure to develop and test nuclear propulsion at scale? Do we accept the safety headaches that come with flying nuclear reactors or huge beamed power systems in space? Do we pour decades of funding into turning maybe into works every time with people on board? Time to Mars isn't set by a cosmic law that says 9 months and no less. It's set by what propulsion we choose to actually field, how much mass we're ready to launch, how much risk we tolerate, and how far we're prepared to stretch our budgets. So when someone asks you, how long would it take us to go to Mars? You don't answer with a flat 9 months, like it's a flight time printed on a ticket. You give them the real picture. You say something like, if we launched on a good window with today's rockets, we'd cruise for about 6 to 9 months, spend maybe a year or more waiting on Mars for the next alignment, and come home on another months-long arc. Realistically, that's a 2 to 3 year odyssey. And the day we reinvent propulsion in a serious way, that number changes, and so does what's possible for our species. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.